Let's do a video about the limiting reactant. What is the limiting reactant? Well, if you need to know, it's the reactant that controls the amount of products produced in a reaction. The idea is that the reaction can only go as far as the limiting reactant allows it to go. Once the limiting reactant is used up, no more products can be formed at all. Because in most reactions, you have two or more reactants. Well, once one of those reactants is gone, the reaction's done. In this scenario that I'm describing, the reaction ends with products and some reactant left over. Unless the ratios are exactly right, you can't use up both of the reactants that you put in. Here's an example. So we're going to calculate the limiting reactant in this reaction. Got some sodium hydroxide and some copper chloride. We're going to make some sodium chloride and some solid copper hydroxide. Say we had 2.113 grams of sodium hydroxide and 4.45 grams of copper chloride. Which one's the limiting reactant? We want to know that, and we want to know how much of one particular product you can make. Now, all limiting reactant problems aren't necessarily this clear. They don't tell you which product to make, but when they are like this, I mean, it really simplifies your life. Because look, it's asking me two questions. Which one is a limiting reactant? And it's asking me how many grams of copper hydroxide I can make. So the smart move is to answer both questions at once. If I do the limiting reactant calculation the right way, I'll figure out how much of each reactant, I'll figure out how much copper hydroxide I can get from each reactant separately. So I'll know which one the limiting reactant is, and I'll know how much copper hydroxide I can make. So I'm going to work with each number separately. First, let's do the sodium hydroxide. So I'm going to write the number down. And the way I do it is to draw these lines. Some people call them train tracks. Call them whatever you want. I don't care. This method works for me. If you don't like it, you can certainly use fractions instead. I'm going to draw a horizontal line, and then I'm going to draw a vertical line. So above and below the line, right? So if things are above and below the line, you divide, but whenever it is, in the same part, either above or below the line, you multiply. Check it out. In order to use the reaction to figure out how much product I can get from the reactant, I need to have moles, because the numbers in the reaction relate to numbers of molecules and numbers of moles. Here I only have grams. So if you start the problem with moles, you're fine. You can go straight from reactant to product. But if you don't, the first thing you need to do is convert from grams to moles. So I figured out the molar mass of sodium hydroxide. Now, all of my numbers come from the Web Elements periodic table. If you go into an internet search engine and you search for Web Elements periodic table, it'll be the first one that comes up. I added up the molar mass of one sodium, one oxygen, and one hydrogen, and I got 39.997 grams. Since that's the molar mass for 1 mole, I write grams in the denominator, and I write moles in the numerator. The reason why I do that is because I want moles and I don't want grams. So when I write it this way, I'm starting with 2.113 grams. I'm going to multiply by 1 mole of NaOH, and I'm going to divide by 39.997 grams of NaOH. Just put them in your calculator one at a time. You don't have to do it all in one shot. Since I have grams of NaOH in the numerator and the denominator, they divide out, and I'm left with moles. Now that I have moles, I can draw another vertical line, and I can use the reaction. The numbers in the reaction give me a ratio between the reactant, NaOH, and the product that I want, the copper hydroxide. So, since I want to go from sodium hydroxide to copper hydroxide, let's put sodium hydroxide in the denominator. I put a 2 there, saying 2 moles, because in the reaction, there's a 2 in front of the sodium hydroxide. Then on the right side, the copper hydroxide doesn't have a number in front of it, so that means it's 1. And check it out. Once again, the moles of sodium hydroxide divides out nice and neatly, and at this point, I'm at moles of copper hydroxide. If the problem just asked me for the limiting reactant, this would be all the farther I'd have to go. But since it's also asking me for grams, I might as well do that calculation at the same time. Again, do both at once, be efficient. One more step, I have to go from moles to grams. So here's another vertical line. And this time, since I want moles of copper hydroxide to divide out, I'm going to put that in the denominator. And again, I used the Webb Elements periodic table. I added up the molar mass of 1 copper, 2 oxygens, and 2 hydrogens, and I got 97.56 grams of copper hydroxide in 1 mole. So I'm going to go through and do the whole calculation. Take my 2.113 grams, multiply by 1, nothing happens, you still have the same number. Then I divide by 39.997, I hit equals in my calculator. Then I go across the next vertical line. Multiplying by 1 doesn't do anything, so I don't worry about that. I divide my answer by 2, I hit equals. Go across the next line. Multiply by 97.56. Don't have to divide by 1 because that doesn't change anything. Hit equals and you get the answer, and it's about 2.577 grams of copper hydroxide. So what this is saying is, if I do this reaction and I use up all of my sodium hydroxide and I have all the copper chloride I need, this is how much copper hydroxide I can make. But I'm not done, because I got to do the same thing for the copper chloride. So I write down my amount of copper chloride, draw my horizontal line, draw my vertical line, and I'm going to follow a similar procedure to what I just did. I add up the molar mass of copper chloride from the same periodic table. I got about 134.446 grams of copper chloride for 1 mole of copper chloride. And again, I'm doing this conversion because I need moles so that I can use the reaction to convert from reactant to product. Draw another vertical line. Moles of copper chloride is going on the bottom because I want to get rid of it. Moles of copper hydroxide is going on the top because that's what I want. Draw another vertical line. Moles of copper hydroxide in the denominator again. Need the molar mass? Okay, it's the same as before. So now, once again, I do the calculations. Just go one at a time. 5.45 divided by 134.446, hit equals. Don't have to multiply or divide by 1. Multiply by 97.56, hit equals. Don't have to divide by 1. There you go. 3.95 grams of copper hydroxide. So, notice that I have 2 answers for the number of grams of copper hydroxide made. Which one do I want? Well, limiting reactant, it's kind of in the name. The limiting reactant is the one that limits the process. It limits how much you can make. So you always want to pick the one that makes less of what you want, because that's what's actually going to happen. See, what this is saying is, once all of the sodium hydroxide is consumed, you're going to have 2.577 grams of copper hydroxide. Once all the copper chloride is consumed, you could have 3.95 grams of copper hydroxide. We're going to go with the lesser one, because once I'm out of sodium hydroxide, I can't react with the copper chloride anymore, and the reaction is done. So, what are my answers? Well, to answer question number 1, the limiting reactant has to be a reactant. It's the reactant that made less product. So I would write NaOH, sodium hydroxide. And how many grams of copper hydroxide can be made? Well, that's this over here, 2.577 grams of copper hydroxide, and that's what I'd put. There you go. That's the beginning of limiting reactant. One basic problem for you to go by. If you like the video, can you leave me a like for the algorithm? And if you want more, you can subscribe. That'd be awesome. And if you have any questions, put them in the comments. I'll answer once I notice it's there. Thanks for watching.